Today we're looking at notes 8-7 FTA, or Fundamental Theorem of Algebra. So we've talked about the Fundamental Theorem of Algebra before, and that it means or states that the degree or highest exponent of a polynomial tells you how many solutions, roots, zeros, or x-intercepts that the polynomial has. So today we're going to be finding all the zeros for each equation. Well, this is nothing new for us. I don't want you to write these down, but this is something that we've done this year. We have found the solutions or x-intercepts of all of these type and many more types of polynomials. We have looked at quadratics by factoring, by quadratic formula, by other means. This cubic here, you would be able to factor out a GCF of x and then either factor or use quadratic formula on the rest. This sum of perfect cubes, we have learned how to factor and go further and solve. Same here with this cubic. It's a 4-term cubic that can be factored by grouping, okay, and then solved from there. This binomial here you should be very familiar with and screaming out at home, that it is a quadratic that is a difference of perfect squares. So we would be able to use that formula to factor this and solve for the x-intercepts or zeros. So this is just a few, not all, but a few of the different types of polynomials that we have learned how to solve so far this year. And today we're going to expand upon that knowledge. So looking at this first number, we have done something similar, but not quite exactly the same. So when I go to find the zero for this, the first thing I'm obviously going to do is plug in 0 for y, because an x-intercept has a y value of 0. Okay, so kind of a tedious step, I know, but is really necessary. Okay, so plug in 0 for y there. And then I noticed that I do have a GCF, so I could go ahead and try to factor. So always worth it to try. So factor out the GCF of x, which leaves me with x to the 4th plus 3x squared minus 4. And then I do have a trinomial inside here, so I am going to try my t-chart. So I know that I would be looking for numbers that multiply to -4, but add to +3, and that is possible. It works with +4 and -1. Okay, so that means that this, and we've done this before, factors to x squared plus 4, x squared minus 1. Okay, because we need a quartic there, so those both, the first terms in each of the binomials have to be x squared. So then to solve, you already know, set each factor equal to 0. So set x equal to 0, set x squared plus 4 equal to 0, and set x squared minus 1 equal to 0 and solve. So that's already solved for x. This I need to subtract 4 each side. So x squared equals -4, square root, the square root of x squared is absolute value of x. The square root of -4 is 2i. To get rid of the absolute value of x, you get x equals plus or minus 2i. Similar here, add 1 each side, square root. So absolute value of x equals 1, and then x equals plus or minus 1. So the fundamental theorem of algebra states that this polynomial should have 5 solutions, and it does. X equals 0, x equals plus or minus 2i, and x equals plus or minus 1. That's 5 total solutions. Okay, so just kind of a refresher there. Let's keep pressing on. So here we have a quintic polynomial of many terms, right? So I've got 1, 2, 3, 4, 5, 6 terms. So I look first for a GCF. I notice I don't have one, and I think, there's 6 terms here. That's an even number. Can I try to group? Well, yes, I first need to plug in 0 for y, and then I'm going to just try to group. Let's see, if I have an even number of terms, it's worth it to try. So I'm going to look at these two, and these two. So the GCF in the first set would be x to the 4th, which would leave me with x minus 1 inside. That distributes back to the original. Okay, GCF here plus my lead negative of -3 x squared, okay, which would leave me with just an x here. Remember, it's got to multiply back to that, and it does. And then -1 here, multiply back to that. Yes, it does. Here I need to factor out the lead negative as well as the GCF of 4. So that would leave me with x minus 1. Does it multiply back? Yes, it does. So this works. You probably can see why it works because my binomials here inside the parentheses match. So I can factor out x minus 1 from each of these groups. When I factor out x minus 1 from this group, I'm left with x to the fourth. If I factor out x minus 1 here, I'm left with negative 3x squared. If I factor out x minus 1 from this group, I'm left with minus 4. And it's strange to think about, but if you distribute that x minus 1 back in, it does get you back to this. Okay, so now this is something I can work with. I just did. I know how to work with this. So it's a trinomial. I can do my t-chart. I would be looking for numbers that multiply to negative 4 and add to negative 3. Oops, add to negative 3. And it's similar to what I had up here, except now I need the 4 to be negative and the 1 to be positive to add and multiply correctly. So I would have 0 equals x minus 1, x squared minus 4, x squared plus 1. And again, same story where you put each factor equal to 0 and solve. So again, this is going to work out pretty similar. So this would be x equals 1. This would be square root both sides, absolute value of x. Okay, so x equals plus or minus 2. Here you get x squared equals negative 1. So square root both sides, this would be absolute value of x equals I. Okay, and then x equals plus or minus I. So for this quintic polynomial of 6 terms, you do have 5 solutions as you would hope. They are x equals 1, x equals plus or minus 2, and x equals plus or minus I. So 5 total solutions. Okay, so hopefully you inquisitive types, all of you hopefully, are thinking, well, that's not going to work every time, right? And you're correct. It's not, okay, because it's not always going to group, right? So let's look at this next example here. If I plug in 0 for y, and then I notice that it is, in fact, an even number of terms, okay, and I try and group. I pull out that GCF of x cubed, that leaves me with x plus 1. Pull out my GCF of 2 here, that leaves me with x minus 2. Are these the same? No, they're not. So, pun intended, we have to regroup. Ha ha ha. Regroup our thoughts and think, okay, well, that's not going to work. What is? Well, this is where technology comes in very, very handy. So I know all along what I've been looking for is solutions, roots, x-intercepts, zeros. Okay, so I have already plugged this equation into the y equals of my calculator, and I'm looking at the graph right now. It looks like I have a root or an x-intercept at negative 2 and at positive 1. It looks like it, but I need to verify it using my table. So I'm going to go to my table and see at negative 2 I do have a 0, and at positive 1 I have a 0. So I've utilized technology. Now I'm going to utilize algebra and my knowledge of said algebra. So I'm going to take this polynomial and I'm going to synthetically divide it by both negative 2 and positive 1 because I see that those are solutions to this polynomial. So I'm going to go ahead and do negative 2 first. We'll just go in order from least to greatest. So I'm going to take this polynomial and divide it synthetically by negative 2 because I know it's a solution. So my coefficients are 1, 1, so that's x to the fourth, x to the third. I'm missing x squared, so I need a placeholder of 0. And then x in constant. Okay, and I'm dividing it by the number, the solution that I got from my calculator, which this should work out. There should be no remainder because it should go in evenly to my polynomial. So 1 here, negative 2 here, negative 1 here, positive 2, positive 2, negative 4, negative 2, positive 4, looky there, 0, just as I expected. Now I should be able to take what I have and I should be able to divide that by 1 because this polynomial also has a solution at 1. So I should be able to take these numbers and divide by 1. So I'm going to drag the first one down, then I get 1 here, 0 here, 0 here, 2 here, multiply there. So 2 and 0. So I'm just doing synthetic division, what you've done before. I'm doing it fast, I know, but you'll probably have to just catch up. Okay, so now let's think about this. This was x to the 4th, okay? So the original problem was x to the 4th. So remember, you go 1 degree down. So this would be x to the 3rd, and what I have now would be x squared. Well, that makes perfect sense because I have two solutions. They are -2 and +1, got them from the calculator. Okay, and that leaves me with a quadratic, 1x squared plus 0x, no reason to write that, plus 2 equals 0. Now I can take that quadratic and get the remaining two solutions for this polynomial. So if I move the 2 over, it becomes negative. Okay, square root both sides, square root. We get absolute value of x equals I square root of 2. So x equals plus or minus I square root of 2. So that gives me my 4 total solutions that I knew I needed to have. Okay, so now let's look at a different example. So here, looking at number 2, I notice 1, 2, 3, 4, 5 terms. Okay, so I can't even try to group. I don't know any other way to factor with that many terms other than grouping, so I'm going to go to the calculator. Again, I've already plugged it into the calculator here, and this is the graph. Okay, so here's what I notice. I notice it looks like a 0, and not only just a 0, but possibly a double. Remember, hits it and bounces back at -1, 2, 3, 4. So I'm going to check out -4, -2 in the table, and +2 in the table. I'm a little unsure about these. They might not be exact. So -4, -2, and +2. Let's see what we get. So -4 is in fact a 0. -2 is not a 0. And +2 is also not a 0. So I'm banking on the fact that that -4 is a double. I hope and pray that it is. So let us see if it is. So I'm going to take -4, remember the 0 I got from my calculator, and I'm going to divide this polynomial by -4. So my coefficients are 1, 8, 13, -24, and -48. So drag that one down, multiply, add, multiply, add, multiply, add, multiply. Okay, it worked once. We knew it was going to at least work once. Let's see if it works twice. All right, -4, so trying it again. 1, drag that first one down always, then multiply, add, multiply, add. Okay, and then we get 0. Yay, it did work twice. So this makes our life so much easier. So we know that -4 works, and not only does it work, but it's a double. Okay, that's 2 out of 4 solutions. I still need 2 more. Well, that's okay because this was x to the 4th. The original was x to the 4th. This is x to the 3rd. Now this is x squared. So we've got 1x squared plus 0x, no reason to write it, minus 3, set it equal to 0, get your other two solutions. So x squared equals 3, square root, absolute value of x equals square root of 3. So x equals plus or minus square root of 3. There's my 2 more solutions. How cool is this? Truly, y'all. Okay, so last one, I'm going to scream through it. All right, last example here. So you look at it, it's 1, 2, 3, 4, 5 terms. Okay, cannot group. Don't know another way to factor. So again, I'm going to utilize technology. I've already got it plugged in here. Looks like I've got roots at -3, +3. Let me double check. -3 is a root. +3 is a root. So I'm going to use synthetic division. I'll start with -3 first. Okay, so 1, 1, -7, -9, -18. Just taking the coefficients from my polynomial. Okay, drag down, then multiply, then add, then multiply, then add, then multiply, then add, and then multiply, and I should get 0, and I do, just as I expect. Okay, never mess with the remainder anymore, it's 0, don't care about that. So then my next root was 3, so bring down, multiply, add, multiply, add, and then multiply and add. Okay, I'm good. But I have a problem. This was x to the 4th. This is x to the 3rd. This is x squared. There's supposed to be 4 roots, and I do have 2 plus or minus 3. Okay, this quadratic will provide me with 2 more. It is quadratic. Here's your problem. It doesn't have 0x. Okay, unfortunately, you've got this ugly quadratic that likely won't be able to be factored. We can try it, but it likely won't. Numbers that multiply to 2 but add to 1, right? That doesn't exist, right? Numbers that multiply to 2 add to 1 don't exist. So unfortunately, what does that mean for you? It means that you need to use quadratic formula. So A is 1, B is 1, C is 2. We've been doing this a lot, so I don't think I need to make this 16-minute video any longer. You can, at home, from here, solve this polynomial using quadratic formula now.